techniques, and let us continue with some more examples. Let us say that we have two equations. Let us say that we have these two equations and two unknowns, and our objective is to solve by Jacobi and Gauss-Seidel method. So, if we write the corresponding formula for iteration, then x1 k plus 1 is equal to 11 minus 10 x2 k. Let us first consider the Jacobi method, and x2 k plus 1 is equal to 11 minus 10 x1 k. Let us say that we have x1 0 is equal to 0 and x2 0 equal to 0 as the initial guesses. So, from here we get x1 1 is equal to 11, x2 2 equal to 11, sorry, x2 1 equal to 11, then x1 2 is equal to 11 minus 10 into x2 1, 11 minus 10 into 11. So, minus 99, x2 2 is 11 minus 10 into x1 k, that is x1 1, that is minus 99. You can see, I mean, let us not go further into these steps, this gives us enough insight that it is diverging. Let us consider the Gauss-Seidel method. The first step is the same, x1 k plus 1 is equal to 11 minus 10 x2 k, x2 k plus 1 is equal to 11 minus 10 x1 k plus 1. So, here also if we take x1 0 is equal to 0 and x2 0 equal to 0, then x1 1 what is x1 1? 11, x2 1 11 minus 10 into 11, so minus 99. In this way, let us calculate maybe one more step, x1 2 is equal to 11 minus 10 x2 1, so what is this? 1001 x2 2 is equal to 11 minus 10 into 1001. So, minus 9999. So, we can see this is diverging, and unlike the case when it converges, Gauss-Seidel converges faster, when it diverges it also diverges faster, what we can see. Now, of course, it does not matter whether it is a Jacobi or the Gauss-Seidel method, there is one fundamental reason for which it diverges, and the reason is that it is not a diagonally dominant system. So, if you find out its spectral radius of convergence, its spectral radius of convergence will become greater than 1. From the rho norm you can easily calculate it. So, if you want to solve this system by using the same methods, what you have to essentially do, you have to reorder the equations. So, you reorder. So, this will become equation 1 and this will become equation 2. Accordingly, let us write the formula. So, x1 k plus 1 is equal to 11 minus x2 k by 10, and x2 k plus 1 is equal to 11 minus x1 k by 10. Now, if you take x1 0 is equal to 0 and x2 0 equal to 0, then x1 1 is equal to 11 by 10, x2 1 is equal to 11 by 10. Next step, x1 2 is equal to 11 minus x2 1, that is 11 by 10 by 10. So, 99 by 100. Then x2 2 is equal to 11, again this is the same, 11 minus x1 1 by 10, that is 99 by 100. So, this is converging to 1 and 1. Let us consider the Gauss-Seidel method. So, x1 k plus 1 is equal to 11 minus x2 k by 10, and x2 k plus 1 is equal to 11 minus x1 k plus 1 by 10. Here also we may start with the initial guess of 0 0. So, x1 1 is equal to 11 by 10, x2 1 is equal to 11 minus 11 by 10 by 10. So, 99 by 100. Then x1 2 is equal to 11 minus 99 by 100 by 10. What is this? 1001 by 1000 and x 22 is equal to 11 minus 1001 by 1000 by 10. What? No, no, no. 4 nines, right? By 10,000. So, what we can see from here is that this is also converging to 1 comma 1, but at a faster rate. So, it is quite clear that what are the important convergence characteristics of the Gauss-Seidel method and the Jacobi's method through this very simple example. Now, in our previous lecture we have discussed extensively about the sufficient condition for convergence, and it is always a question whether a method will automatically satisfy the sufficient condition for convergence or not. In many cases for some special matrices, fortunately the method always satisfies the sufficient condition for convergence. For example, let us consider this as a problem. Show that for a symmetric and positive definite coefficient matrix, the Gauss-Seidel method always satisfies the sufficient condition for convergence. I will partially work it out for you and leave the remaining on you as an exercise. So, the situation is that we are interested for the Gauss-Seidel method. What is the M matrix for the Gauss-Seidel method? Minus L plus D inverse U. To show that it satisfies the sufficient condition for convergence for a matrix, coefficient matrix A, which is symmetric and positive definite, we have already seen that what do we mean by a symmetric matrix and a positive definite matrix. Positive definite matrix has many interesting properties, we will come into that later on, but just to refresh that if you have a vector x, if you have a positive definite matrix x, then x transpose Ax is greater than 0, or you can put a greater than or equal to 0. So, this means it is positive definite. Positive definite matrices have positive diagonal elements and positive principal minors. They have certain several interesting and important properties. Now, so if some of the diagonal elements appear to be negative, you should suspect that it is not a positive definite matrix. And symmetric matrix A means A transpose equal to A for symmetric. Now if V is an eigen vector, then we have mV is equal to minus lambda L plus D inverse u V. Why we are bringing the eigenvalue and eigenvector into the picture? Because it is the mod of lambda, max of that will dictate whether it is satisfying the sufficient condition for convergence. So we have to bring the lambda into the picture. Now so this is equal to, sorry, this is equal to lambda into V, okay. So now you can write u into V multiplying pre-multiplying both sides by L plus D is minus lambda L plus D into V. Because it is a symmetric matrix, U is nothing but equal to L transpose. Because A is a symmetric matrix, it is symmetric with respect to the diagonal. So U and L are related by U equal to L transpose. So this is one thing that we will keep in mind, let us call it equation number 1. Also UV equal to this one. Now you can write it in terms of AV, here it is U into V. If you want to write it in terms of A into V, you have to add L plus D into V, because L plus D plus U is A. So U plus L plus D V is equal to minus lambda then plus 1 you add L plus D into V both sides, which means AV is equal to 1 minus lambda L plus dV. So if you want to calculate what is V transpose AV, now let us calculate the transpose of V transpose AV. If you calculate V transpose AV transpose, then it is as good as AV transpose into V transpose transpose. It is we have written A into B transpose equal to B transpose into A transpose. So this is equal to V transpose A transpose, and V transpose transpose is V. It is same because A and A transpose are the same. So if you take transpose of 2, then what you can write? One minus lambda V transpose L plus D. So, transpose of 2 is same as 2, that means 1 minus lambda V transpose L plus D V is equal to its transpose. So, when we take a transpose of a matrix and then find the eigenvalue, then what can be the eigenvalue? Does it remain the same? It may remain the same, but we can generalize it a little bit. Like for example, let us consider a 2 by 2 matrix, say A, B, C, D. So, if you want to find out its eigenvalues, what you do? You write A minus lambda, B, C, D minus lambda, determinant, set determinant equal to 0. If you have the transpose of this one, the same equation governing the eigenvalue will be valid, but it is a quadratic equation, it has 2 roots. So, it could be that for the original matrix one of the roots was the lambda, and for the transpose the corresponding conjugate root was the lambda. So, in general you could write that the transpose may have an eigenvalue which is lambda bar, which may be either the same or the conjugate of that. If it is a complex number, it can be a complex conjugate. So, we just generalize it by giving it a name lambda bar, keeping in mind that it can also be same as lambda. Okay. So, 1 minus lambda bar then the transpose of this one. So, V transpose into L plus D transpose into V. So, this is nothing but equal to 1 minus lambda bar V transpose L transpose V plus 1 minus lambda bar V transpose D transpose and D are the same, it is a diagonal, V transpose dV. And from equation 1 we can write L transpose V in terms of L plus D into V. So, this from equation 1 we can write 1 minus lambda bar in place of, so we multiply equation 1 by V transpose, so that becomes minus lambda into V transpose L plus dV and then the original term. This is using 1. So, you can see in the left hand side and in the right hand side you can take V transpose L plus dV as common in the first two terms. So, in the left hand side and in the right hand side the first term you have V transpose L plus dV common. If you take that as common, then you have 1 minus lambda plus lambda minus lambda into lambda bar. Into V transpose L plus dV is equal to 1 minus lambda bar into V transpose dV. So, next is we can write, see we are interested to write everything in terms of A and D, because if A is a positive definite matrix then V transpose AV is greater than 0, that we know, and also V transpose DV is greater than 0 because the diagonal elements are all positive. So if we want to write V transpose L plus dV in terms of V transpose AV, then we need to use equation number 2. So we can write 1 minus lambda into lambda bar in place of V transpose L plus dV, it is V transpose AV by 1 minus lambda is equal to 1 minus lambda bar V transpose dV. This is using 1, sorry, using 2. If you consider lambda and lambda bar as complex conjugates, first of all let us write this one as V transpose dV by V transpose AV is equal to 1 minus lambda lambda bar by 1 minus lambda into 1 minus lambda bar. Let us take the simple case when lambda bar is equal to lambda. We have seen that it is possible that by transposing you get the eigenvalue which is same as the eigenvalue without transposing. So if lambda is equal to lambda bar, then this becomes 1 minus lambda square by 1 minus lambda whole square. Now V transpose dV is greater than 0, V transpose AV is greater than 0 for positive definite A, therefore this is greater than 0, in general greater than equal to 0. That means lambda square is less than or equal to 1 or mod of lambda max is less than equal to 1. Denominator is always positive. Okay. So if the eigenvalue remains exactly the same, it is very trivial to show that it satisfies the sufficient condition for convergence. If on the other hand, if lambda bar is complex conjugate of lambda, that is another example. Then we can write lambda into lambda bar is mod lambda square, right. If lambda and lambda bar are complex conjugate to each other, then lambda into lambda bar is mod lambda square, and 1 minus lambda into 1 minus lambda bar is positive, like for example let us say lambda is equal to A plus IB, then lambda bar may be A minus IB, complex conjugate. So 1 minus lambda is 1 minus A minus IB and 1 minus lambda bar is 1 minus A plus IB. So the product is 1 minus A square plus B square, that is positive. So in either way it can be shown that mod of lambda max is less than 1, less than equal to 1. So that it satisfies the sufficient condition for convergence. Anyway, I thought that I will leave it to you as an exercise, but I completed this, so I will leave something else on you as an exercise. Now the next issue is, we have seen the convergence characteristics of the iterative methods. Are there any means by which you can improve on the convergence characteristics? And there are certain ways of doing that, and those methods are called as relaxation methods. The whole idea of a relaxation method is to improve the convergence characteristics of a particular iterative method. So let us consider the Jacobi's method. So in the Jacobi's method, if you write it in terms of the indices of the matrix, it is AII xi k plus 1 is equal to minus summation of a I j x j, j is not equal to I plus b I k, right. So, remember it is L plus D plus U which is the matrix A, this corresponds to D and this corresponds to L plus U. In the Jacobi's method you have L and U together with the same level of iteration. So, xi k plus 1 you can write minus summation of a I j, j not equal to I by a I I x j k plus b I by a I I. Let us try to write this xi k plus 1 in terms of xi k. So, what we do is we write this as a I I by a I xi k, then we also have to subtract a I I by xi a I k. So, if we combine that with this negative term, then what we get minus summation of a I j by a I I, but now j can be equal to I. So, one extra term we add. This is clear to everybody. So, what we have done? We have added one term which is a I I by a I I x I k, that we have subtracted, and when we have subtracted that means we have also considered j equal to I. So, that j not equal to I we have relaxed. So, k plus 1 is equal to x I k plus x tilde, where x tilde equal to b I minus summation of a I j x j k by a I I. So, in the relaxation method what we do? We multiply this x tilde with a factor alpha which we call as relaxation parameter or relaxation factor. This relaxation factor can be a number which is different from 1. If it is equal to 1, it will mean the original Jacobi's formula. If it is different from 1, it will be a different formula. Now, the big question comes that how can we temper a formula like this? So, if you make this as alpha which is not equal to 1, you are tempering a formula which you have derived from certain fundamentals, still you expect that you will get the final solution. Why? Because you expect something to occur which is very intuitive, that if convergence occurs then xi k plus 1 will be equal to xi k, and then the choice of this alpha is irrelevant. So, what it basically does is it can take you to the same convergence but through a different route of iterations, and the route of iterations is decided by this relaxation factor. So, this is called as a relaxation method. So, depending on its value it can sometimes accelerate the convergence, sometimes if the value is not chosen very judiciously it can slow down the convergence process. So, it has a control over the rate of convergence. Now, let us try to write the same thing for the Gauss-Seidel method. aii xi k plus 1 is equal to, now there are two parts, minus summation of aij xj k, one is k plus 1, another is k. Now let me just write j is equal to 1 to I minus 1, does it belong to k plus 1 or k? This is the L part, right. So L plus D that gets combined with k plus 1. So this is D with k plus 1, this is the L part, the lower triangular matrix part that gets coupled with k plus 1. Then so this is for j equal to I plus 1 to n plus bi. So you can write xi k plus 1 is equal to, just like the previous case, you add aii by aii xik minus summation of aij xj k plus 1, j is equal to 1 to I minus 1 minus summation of aij xj k, now j equal to I to n, because you have added one aii plus bi. So you have xi k plus 1 is equal to xi k, these have divided by aii, right. Plus x tilde, where x tilde is equal to bi minus summation of aij xj k plus 1 by aii, j is equal to 1 to I minus 1 minus summation of aij xj k, j is equal to 1, j is equal to I to n by aii, bi by aii also, right. So here also you can introduce the relaxation parameter alpha, and this particular method, when it is derived originally from the Gauss-Seidel method with a relaxation parameter, this is called as SOR method or successive over relaxation method. Now can you identify that what is the significance of this x tilde? This x tilde is equal to 0 when the convergence has occurred, and this x tilde is nothing but equal to b minus ax during the iteration. So it is a residual. So x tilde is a normalized residual, it is b minus ax normalized with respect to the diagonal coefficient. So this is a representation of the residual, and we know that when it converges, technically the residual should vanish, and therefore when it converges it does not matter what alpha you have taken, but the path by which it will travel during iterations for convergence, that will be strongly dependent on the choice of the parameter alpha. This is one very interesting and important inference, and one can choose alpha in a way to accelerate convergence very nicely in the successive over relaxation method. So now I give you something as a homework to try, taking a numerical example. This is a homework problem. Taking a numerical example of a 2 by 2 system show that for SOR method alpha optimum is equal to 2 by 1 by 1 minus the square of the spectral radius of convergence for the Gauss-Seidel method for the matrix M. Okay. So what you have to do, you have to take any numerical example or take a simple form of a 2 by 2 matrix. Some of the entries you may take 0, but you may not also take that. So from that you write the corresponding M matrix, find out the corresponding spectral radius of convergence, and with different choices of the spectral radius of convergence, that means with different choices of A, you show that out of all possible choices the optimum alpha that will give you the best possible convergence is this one. Okay. Of course this can be even shown analytically, but it is much more convenient to show it through some numerical examples. So you can work out a few numerical examples with a few choices of the coefficient matrix A, and you can show this by showing that you require the minimum number of iterations to achieve convergence when the value of alpha is equal to this one. So that will give you the fastest rate of convergence. Now we have learned some iteration methods and some elimination methods by now. Question is what do we prefer in CFD applications out of these two if you have a choice. Very commonly we use the iteration methods as a preference. We will see later on that it is not always true, sometimes a combination of these is what we look for, but in general iterations are preferred. And why? First of all, so some preferential characteristics of the iterative methods. The first and foremost reason is that the iterative methods can very easily handle non-linearities in the system, can accommodate non-linearities very easily. Just let us take an example, it need not be an example of a differential form, just let us consider that you are interested to solve ax square plus bx plus c equal to 0. This you can write as ax into x plus bx plus c equal to 0, let us call it xk plus 1 and this x as xk, just some arbitrary iterative formula. This is just for illustration, do not take it as a very rigorously derived formula, but what you can see from here is that you can express xk plus 1 explicitly in terms of xk, and it is a linear formula in xk plus 1. You can even write this as xk plus 1 for the coefficient b in place of xk you can write it xk plus 1, still it remains linear in xk plus 1, although the original equation was non-linear. So what you are doing is you are breaking x square as x into x, in one of those x's you are using the old value. See, we can write a formula in some mathematically rigorous way, but it is very important to appreciate that essentially what we are doing, we are replacing the variable with some, we are assigning the variable with some value. What is that value? A part of that is some old value, so that when you write it in this way it is a pseudo linear form in terms of xk plus 1. So in an iterative environment you can very easily accommodate non-linearities, and storage overhead is also less for iterative schemes. Storage means computer storage overhead for the data is less for iterative schemes. But are all aspects of iterative schemes so good? We have to assess. One of the important assessments is that if you refine the mesh spacing, your rate of convergence decreases. In our previous lecture we worked out an example where we decrease the mesh size from say 10 to the power 3 by 10 to the power 3, we coarsened it to 10 to the power 2 by 10 to the power 2, and we showed that rate of convergence increases. So that means you have, if you use a defined mesh, and many times we use a defined mesh to get a more accurate solution, that is the natural tendency, but at that cost what we sacrifice is that now we have reduced rate of convergence. So we will be getting more accuracy hopefully, but with a much reduced rate of convergence which perhaps we are not able to afford. So what we do with that? So simply we cannot get rid of the method because the method is otherwise good, but we may have to adapt this method for two types of systems, for one finer mesh and for a coarser mesh, and then transform the method from one mesh to the other back and forth, and this particular method is known as multi-grid method. So we will try to develop an outline of the multi-grid method, but before doing that we should appreciate certain things, that how do the errors propagate in an iterative scheme. So in an iterative scheme you have the mesh size like this may be a fine mesh and this may be a coarse mesh as an example. You can refine a coarse mesh very easily. Let us say this is a refined version of a coarse mesh. Now if you make a spectral analysis of the errors, then errors in an iterative scheme have wavelengths which are multiples of the mesh size. So let us note that first. So error components have wavelengths multiples of the mesh size. What is the largest wavelength possible? That is the domain size itself. So if you have a defined mesh, let us say that you have a defined mesh, then what is the maximum multiple of the smallest mesh size that is possible for the wavelength? You have 4 multiples of that. If you had a coarse mesh you could have maximum only as 2 multiples. So what happens is during iterations small multiple wavelengths, errors corresponding to small multiple wavelengths, error components basically, error components corresponding to small multiple wavelengths. Small multiple wavelengths tend to get reduced quickly. Get reduced rapidly. When we say rapidly, we mean more rapidly than the large multiple wavelengths as compared to large multiple wavelengths. So, if you are solving a problem in a fine mesh, with iterations you are taking care of the small multiple wavelengths error corresponding to that, but the large error corresponding to the large multiple wavelengths they tend to remain, and that is why you require more number of iterations to achieve the convergence. Now in multi-grid method what is done is, first we consider a refined mesh. First consider a refined mesh. So in the refined mesh you solve Ax equal to b. You have to keep in mind that because of the non absorption of the large wavelengths, large multiple wavelengths, errors will remain. So what you get is A approximate which is not equal to b. So Ax minus x approximate will be equal to b minus Ax approximate equal to r, which is the residue, that is Ae equal to r. Now to absorb the errors in the large multiple wavelengths, you now are interested to solve for this Ae equal to r by transferring the system to a coarse mesh, not a refined mesh. Then transfer the system to a coarse mesh. How do you transfer it to a coarse mesh from a fine mesh? Maybe you do averaging. Let us say that you have coefficients like this, and when you have coefficients like this, say, or let us say you have coefficients like coefficients at these points. Now you are interested to find out coefficients at which points in the coarse mesh, coefficient at this point. So that you may consider as an average of the coefficients between these 2 points, something like that. So at a particular point you can consider coefficient as an average of the neighbors, information of which now is lost. So transfer the system to a coarse mesh. Then in the coarse mesh you solve for Ae equal to r with E0 equal to 0. So you have a new E, a new A which you have formed by using the refined mesh. You are interested to solve for E, for that initial guess is 0, and the residual you have already got from the refined mesh, and that you can average just like how you did average for the coefficient A. So, from here you can get what is E, then transfer this E back to the defined mesh. So, when you transfer this E back to the defined mesh, then you have to use some interpolation techniques, because you have E's for the coarse mesh points. So, you have E's for this, you have E for maybe this point, you have E for this point, but not for this point or not for this point, because these were not the points of agenda for your coarse mesh. But now when you define mesh, you have to calculate E here, you have to calculate E here. So, for that you can use some interpolation technique, maybe a linear interpolation. So, transfer, so when you transfer here you require some averaging technique, and when you transfer here you require some interpolation technique, and then you can write that if you know the error, then you have nu x is equal to x old plus error. X old was x approximate, this is x old, because x minus x old is error. Okay. So, you can update your x by considering the previous x plus the error. So, what you have done essentially is that you have taken care of the large wavelength error by transferring it to a coarser mesh. The small wavelengths were already taken care of during iterations in the finer mesh, but large wavelengths were not taken care of, that is why you have to transfer it to a coarser mesh and take care of the large wavelength error and then bring it back to the refined mesh. So, this in this way you are using grids of multiple sizes to get an accurate solution, and this technique, that is why, is known as a multi-grid technique. So, there are similar such advanced techniques. We will not go into more details of that, and we will stop here today. In the next class we will try to look into some techniques where we combine the iteration and the elimination methods, and then we will go for the gradient search method. Thank you.